There are moments in life when the universe stops hiding and shows you something it was never required to explain. A light that should not exist, a glow with no source, a dance with no dancer. And in those moments, you realize that the world you thought you understood is far stranger, far more beautiful, and far more connected than you ever imagined. Tonight, we're going to talk about one of those moments, a phenomenon so mysterious that ancient civilizations built entire mythologies around it, so beautiful that modern travelers cross continents just to witness it for a single night, so powerful that it can disrupt satellites, knock out power grids, and remind us that Earth is not a safe harbor floating in empty space, but a small magnetic island in a river of fire flowing from the sun. The northern lights, aurora borealis, the fox fires, the bridge to Valhalla, the spirits dancing. Humanity has given it 1,000 names, but we have only recently begun to understand what it truly is. And the answer, the real answer, is more extraordinary than any myth we ever created. Imagine this. You're standing in the middle of nowhere, northern Alaska, perhaps, or the remote coastline of Iceland. It is winter, deep winter, the kind where your breath freezes before it leaves your lips. The temperature is 20 degrees below zero. The wind has died completely. The world is silent in a way that city dwellers never experience. Not quiet, silent. The kind of silence that makes you aware of your own heartbeat. Above you, the sky is black. Not the murky gray black of light polluted suburbs, but true black, the black of deep space pressing down, and scattered across that blackness are more stars than you have ever seen. The Milky Way stretches overhead like a river of light. You can see the curve of it, the depth of it, the sheer overwhelming scale of the galaxy you live in. You have been standing here for an hour. Your toes are numb, your fingers ache. Despite the gloves, you are beginning to wonder if tonight will be one of those nights where nothing happens, where you drove 3 hours into the wilderness, set up your camera, and waited in the cold for a sky that remains stubbornly empty. And then, just as you are about to give up, you see it, a faint glow on the northern horizon. At first, you think it might be a distant town, some settlement you did not know existed. But the glow is green, a pale, sickly green that does not match any artificial light you have ever seen. And it is moving. You watch as the green light begins to spread. It climbs higher into the sky, stretching upward like fingers reaching from the horizon. The light is not solid. It shimmers. It pulses. It looks almost liquid, like someone spilled luminescent paint across the dome of the sky, and it is slowly dripping downward. Within minutes, the faint glow has transformed into curtains, massive vertical sheets of light, hundreds of miles tall, stretching from horizon to horizon. They ripple and wave as if caught in a wind you cannot feel. The green deepens, becomes richer, more vivid, and then, at the top edge of the curtains, you see a hint of red, a dark crimson fringe that flickers in and out of existence. You stand frozen, not from the cold anymore, but from something else. Wow, maybe, or fear, or the sudden overwhelming awareness that you are watching something that originates 93 million miles away, something that has traveled across the empty vacuum of space to paint light across Earth's magnetic field, something that should not be visible, should not be beautiful, should not exist at all in any rational universe. But it does exist. It is happening right now, above your head, and you are one of the few human beings on Earth in this exact moment who can see it. The curtains begin to move faster. They fold and unfold. They pulse brighter, then dimmer, then brighter again. A vertical column of light shoots upward, so straight and perfect it looks artificial. More curtains appear to the east, spreading the display across half the visible sky. The snow around you takes on a green tint. You look down at your hands and see they are glowing. And then, for just a moment, the aurora explodes. It spreads directly overhead, radiating outward from a point above you in a perfect circle, a corona. You are standing at the center, looking up into a tunnel of light that seems to pierce through the atmosphere and connect Earth directly to the cosmos beyond. The green is so bright you can read by it. The red intensifies. Streaks of purple appear at the edges. Your breath catches. Your heart pounds. You forget about the cold. Forget about your numb fingers. Forget about everything except this moment. This impossible, beautiful, terrifying moment when the universe decided to put on a show and you were here to see it. And then, just as suddenly, it begins to fade. The corona collapses. The curtains weaken. Within 5 minutes, the sky is dark again, empty except for stars. The aurora has vanished as mysteriously as it appeared, leaving you standing in the snow, wondering if what you just witnessed was even real. But here is what you do not know. Here is what almost no one standing beneath the northern lights understands in that moment of awe. The light show you just watched is not just beautiful, it is a warning, a visible manifestation of an invisible war being fought at the edge of space. A battle between the sun's fury and Earth's magnetic shield. A battle that has been raging for 4.5 billion years and will continue long after humanity is gone. And the story of how that battle creates light, how particles from the sun travel across the solar system to collide with atoms in our atmosphere, how Earth's magnetic field funnels and guides and shapes those collisions into dancing curtains, is a story that begins not here on Earth, but on the surface of a star, our star, the sun, where right now, at this very moment, something violent is happening. Hey guys, tonight we begin with one of nature's most hypnotic phenomena, the northern lights, a display so peaceful, yet so powerful, that it has captivated humanity since we first looked up at the night sky. From the science of solar winds to the magnetic embrace of our planet, their story is one of cosmic connection, ancient wonder, and breathtaking beauty. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you are tuning in from and what time it is for you. It is always fascinating to see who is joining us from around the world. Now, dim the lights, maybe turn on a fan for that soft background hum. Get into your blanket, and let's ease into tonight's journey together. 93 million miles away from the frozen Arctic, from the traveler standing in the snow, from Earth itself, there is a sphere of nuclear fire, the sun, our star. The reason anything exists in this corner of the galaxy, and right now on its surface, something catastrophic is building. The sun is not what most people imagine when they think of a star. It is not a solid ball of fire floating in space. It is not even burning in the traditional sense. The sun is a sphere of plasma, superheated gas, so hot that electrons have been stripped from their atoms, creating a sea of charged particles, hydrogen nuclei, and free electrons swirling in a magnetic chaos that generates energy through nuclear fusion. At the core of the Sun, where temperatures reach 15 million degrees Celsius, hydrogen atoms are crushed together by gravity. They fuse, combining to form helium and releasing tremendous amounts of energy in the process. This energy radiates outward, taking hundreds of thousands of years to travel from the core to the surface. By the time it emerges, it has transformed from gamma rays to visible light, the light that warms our planet and makes life possible. But the sun does not just produce light, it produces particles, enormous quantities of charged particles that stream outward in all directions. This is the solar wind, a constant flow of electrons and protons ejected from the sun's outer atmosphere, the corona, and sent racing through the solar system at speeds between 300 and 900 kilometers per second. Under normal conditions, this solar wind is relatively calm. It flows steadily outward, filling the space between planets with a thin plasma. Earth sits in this wind constantly, every second of every day. The particles wash over our planet like water flowing around a stone in a stream. Most of them are deflected harmlessly away by Earth's magnetic field. We do not even notice they are there. But the sun is not always calm. The sun has moods, cycles, periods of intense activity when its magnetic field becomes twisted and unstable. These active periods create something far more dangerous than the steady solar wind. They create solar storms. Right now, on the surface of the sun, a sunspot is forming. Sunspots are dark patches, cooler regions where the sun's magnetic field has broken through the surface and suppressed the convection that normally carries heat upward. They look small through a telescope, but they are enormous. This particular sunspot is 3 times the diameter of Earth, and it is growing. Around the sunspot, the magnetic field lines are twisting, building tension. Imagine taking a rubber band and twisting it tighter and tighter. Eventually, something has to give. In the sun's case, what gives is the magnetic field itself. It snaps, reconnects, and releases an enormous burst of energy in an instant. This is a solar flare, a sudden brightening on the sun's surface as millions of tons of plasma are heated to tens of millions of degrees. The flare releases as much energy as billions of nuclear bombs detonating simultaneously. X rays and ultraviolet light surge outward, crossing the distance to Earth in 8 minutes. When they hit our atmosphere, they cause radio blackouts on the daylit side of the planet. Pilots lose communication. GPS signals degrade. But this is only the beginning. Following the flare, something even more dramatic occurs: a coronal mass ejection. A CME, the sun's corona, literally tears open, and a massive bubble of plasma erupts outward into space. This is not the steady solar wind. This is a tsunami, a wave containing billions of tons of charged particles, all carrying the sun's magnetic field with them, all traveling at speeds up to 3,000 kilometers per second. And this particular CME is headed directly toward Earth. The plasma cloud expands as it travels, growing wider and more diffuse. It moves through the solar system like a ghost, invisible to the naked eye, detectable only by satellites equipped to measure magnetic fields and particle densities. Inside the cloud, electrons and protons spiral along magnetic field lines, trapped in a structure that stretches millions of kilometers across. On Earth, scientists at the Space Weather Prediction Center see the data come in from satellites positioned between the Sun and our planet. The readings are clear. A major geomagnetic storm is coming. They issue warnings. Power companies are alerted to prepare their grids. Airlines are advised to reroute flights away from polar regions where communication could be disrupted. Satellite operators put their equipment into safe mode. But for the aurora hunter standing in the snow in Alaska, these warnings mean something entirely different. They mean tonight is going to be spectacular. The CME takes approximately 17 hours to reach Earth. During that time, it travels across the vast emptiness of interplanetary space, past Mercury's orbit, past Venus, through the region where Earth circles the Sun, and then, early in the evening, just as the sun sets over Alaska and darkness begins to spread across the Arctic, the leading edge of the plasma cloud slams into Earth's magnetosphere. This is the moment everything changes. This is when the battle begins. The sun's plasma, carrying its twisted magnetic field, crashes into Earth's magnetic field like a wave hitting a seawall. The impact compresses the magnetosphere on the day side, pushing it inward. Earth's magnetic field responds, flexing and bending under the pressure. But Earth's magnetic field is strong. It does not break. Instead, it redirects the incoming plasma, channeling it around the planet. Most of the particles are deflected, sent flowing past Earth and continuing their journey deeper into the solar system. They will travel outward until they reach the heliopause, the boundary where the sun's influence finally ends and interstellar space begins. But not all the particles are deflected. Some find their way in because Earth's magnetic field, strong as it is, has weak points. Near the north and south poles, the field lines converge. They dip down toward the surface, creating openings, funnels, pathways through the magnetic shield. The charged particles from the sun spiral along these field lines, following the invisible pathways downward. Electrons and protons, still carrying tremendous energy from their journey across the solar system, are pulled toward the polar regions. They accelerate as they descend, guided by the magnetic field toward the upper atmosphere. And as they descend, they enter a region where Earth's atmosphere is still present, but incredibly thin, a region between 60 and 600 kilometers above the surface, where oxygen and nitrogen molecules float in the near vacuum of space. This is the thermosphere, and this is where the magic happens. This is where the particles from the sun, after traveling 93 million miles, after riding the solar wind for nearly a day, after being funneled through Earth's magnetic field, finally collide with something solid, with atoms, with the very air that makes life on Earth possible. And in those collisions, in those brief moments of impact, energy is transferred. Electrons are excited, atoms are ionized, and when those atoms return to their normal state, they release the energy they absorbed as light, visible light, green light, red light, purple light. The northern lights are born. But how exactly does this happen? What is occurring at the atomic level when a particle from the sun strikes an oxygen molecule? Why does the aurora glow green instead of blue or yellow? Why do the lights move and dance instead of remaining stationary? And why do they only appear near the poles? These questions have answers, answers that take us deep into the physics of atoms, the behavior of magnetic fields, and the strange quantum rules that govern how light is created. And as we explore these answers, You will see that the northern lights are not just beautiful, they are a visible manifestation of forces that exist everywhere in the universe, but are rarely seen. A window into processes that govern stars and galaxies and the very structure of matter itself. The traveler in the snow does not know any of this. They only know that the sky is beginning to glow, that something impossible is happening above their head, that tonight the universe is about to put on a show, and standing there in the cold breath freezing in the air, they watch as the first faint green curtains begin to appear on the horizon. The story is just beginning. The collision between the solar wind and Earth would be catastrophic if not for one crucial fact. Our planet has a defense system, an invisible force field that has been protecting life for billions of years. Without it, Earth would look like Mars, a dead, barren rock with its atmosphere stripped away by solar radiation. But we are lucky. Deep, deep beneath our feet, something extraordinary is happening. Beneath the crust, beneath the mantle, at the very center of Earth, lies a core of molten iron. This iron is not sitting still. It churns, it flows, it moves in massive convection currents driven by the residual heat from Earth's formation and the decay of radioactive elements. This movement is chaotic, turbulent, like a storm that has been raging for over 4 billion years. And this storm of molten metal generates something invisible yet powerful, a magnetic field, the same force you feel when you hold two magnets together, but on a planetary scale. Earth's magnetic field extends far into space, creating a bubble around our planet called the magnetosphere. This bubble is enormous. On the side facing the sun, it extends about 10 Earth radii outward. On the side facing away, it stretches into a long tail that reaches past the orbit of the moon. The shape of this magnetic bubble is not uniform. It looks like a teardrop. The side facing the sun is compressed, squashed by the constant pressure of the solar wind. The opposite side is stretched out, elongated into a tail that extends hundreds of thousands of kilometers into space. This shape is dynamic, constantly changing as the solar wind fluctuates and as Earth rotates. But the most important feature of the magnetosphere is not its size or shape. It is the way the magnetic field lines are arranged. These field lines emerge from the south magnetic pole, arc through space, and converge back down at the north magnetic pole. Near the equator, the field lines are nearly horizontal, parallel to the surface, but near the poles, they are vertical, pointing straight down into the atmosphere. This arrangement creates a natural defense. When charged particles from the solar wind approach Earth, they cannot easily cross magnetic field lines. The particles are themselves charged, which means they interact with magnetic fields. They spiral around the field lines, trapped by the magnetic force. Most of them are simply deflected around Earth, following the field lines as they curve away from the planet. Imagine water flowing around a rock in a river. The rock creates a disturbance in the flow. Awake, the magnetosphere does the same thing to the solar wind. Most particles flow around Earth harmlessly, continuing their journey into deeper space. We never see them. We never feel them. They might as well not exist. But the magnetosphere has vulnerabilities. Near the poles where the field lines converge and point downward, there are openings. The particles can follow these field lines down into the atmosphere. They spiral along the magnetic pathways, accelerating as they descend, guided toward the polar regions like water swirling down a drain. This is why the northern lights appear near the poles. This is why you have to travel to Alaska or Scandinavia or Iceland to see them. The aurora forms in a ring around each magnetic pole, a region called the auroral oval. This oval shifts and changes size depending on solar activity, but it is always centered on the magnetic poles, not the geographic poles. There is a difference. Earth's magnetic poles are not in the same location as the geographic poles. The North Magnetic Pole is currently located in the Canadian Arctic, moving northwest at a rate of about 50 kilometers per year. Yes, it moves. The magnetic field is generated by flowing molten iron, and that flow changes over time. The poles wander. They have even reversed completely many times in Earth's history, with north becoming south and south becoming north. The last reversal happened about 780,000 years ago. But for now, the poles are where they are, and the auroral oval follows them. The oval is typically about 3,000 kilometers in diameter, centered on each magnetic pole. Under quiet conditions, the aurora remains within this oval, visible only to people living at high latitudes. But when a geomagnetic storm hits, when a coronal mass ejection slams into the magnetosphere with tremendous force, everything changes. The magnosphere compresses. The pressure from the incoming plasma pushes the dayside magnetic field inward, sometimes as close as 6 Earth radii. Energy builds up in the magnetotail on the night side, stored in the twisted magnetic field lines. And then, like a rubber band snapping back, the field lines reconnect. They release their stored energy in a process called a magnospheric substorm. During a substorm, enormous quantities of particles are suddenly accelerated toward Earth. The auroral oval expands, sometimes dramatically. Auroras that were confined to the Arctic now appear over Canada, over the northern United States, over Scotland and Scandinavia. In extreme cases, during massive geomagnetic storms, the aurora can be seen as far south as the Caribbean. The most famous example occurred in September 1859, the Carrington event, named after astronomer Richard Carrington, who observed the massive solar flare that triggered it. The resulting geomagnetic storm was so powerful that auroras were seen in Cuba, in Hawaii, and Colombia. People in the Rocky Mountains woke up at midnight thinking it was dawn because the sky was so bright. Telegraph systems around the world went haywire. Operators received electric shocks. Telegraph paper caught fire. Some systems continued to send and receive messages even after being disconnected from their batteries, powered solely by the electrical currents induced in the wires by the geomagnetic storm. If a Carrington level event happened today, the damage would be catastrophic. Power grids could fail across entire continents. Satellites would be damaged or destroyed. GPS systems would become unreliable. Communications would be disrupted. Some estimates suggest that repairing the damage could take months or years and cost trillions of dollars. This is not science fiction. This is a real threat that scientists and governments are actively working to prepare for. But most geomagnetic storms are not Carrington level events. Most are moderate, producing beautiful auroras without causing significant damage. And the process that creates these auroras, the mechanism by which charged particles become visible light, is a story of atomic physics that happens in a fraction of a second. When an electron from the solar wind, guided by Earth's magnetic field, descends into the upper atmosphere. It is moving incredibly fast, tens of thousands of kilometers per second. In some cases, it carries kinetic energy from its journey across the solar system. And when it collides with an atom of oxygen or nitrogen floating in the thin air of the thermosphere, that energy has to go somewhere. The collision is not like two billiard balls hitting each other. These are quantum particles operating under quantum rules. When the electron strikes an oxygen atom, it transfers some of its energy to the oxygen's electrons. Those electrons jump to higher energy levels, what physicists call excited states. The atom is now holding more energy than it normally would, and it is unstable in this configuration. Atoms do not stay excited forever. They want to return to their ground state, their lowest energy configuration, and the only way to release the excess energy is to emit a photon, a particle of light. The color of that light depends on how much energy is being released, which depends on which energy levels the electrons are jumping between. Oxygen atoms in the thermosphere at altitudes between 100 and 150 kilometers emit green light when they return from their excited state. The wavelength is 557.7 nanometers, a very specific shade of emerald green. This is the most common aurora color because this is where most of the collisions happen. The air is thin enough that the solar particles can penetrate easily, but thick enough that there are plenty of oxygen atoms to collide with. At higher altitudes, above 200 kilometers, oxygen atoms emit red light at 630 nanometers. These red auroras are fainter and less common because the air is so thin at these altitudes that collisions are rare. But during strong geomagnetic storms, when high energy particles penetrate deep into the magnetosphere, the red auroras can become quite bright, creating a stunning display of crimson curtains above the green. Nitrogen molecules add blue and purple to the palette. When nitrogen is ionized, losing an electron in the collision, it emits blue light at 428 nanometers. When nitrogen is excited but not ionized, it glows purple. These colors typically appear at the lower edges of the aurora, below 100 kilometers, where nitrogen is more abundant than oxygen. The result is a spectrum, a natural light show created by atomic physics, painted across the sky in real time. And the beauty of it is that every photon you see, every tiny particle of light, represents one collision between a particle from the sun and an atom of Earth's atmosphere. Billions upon billions of these collisions happening simultaneously, creating curtains of light that can stretch for thousands of kilometers. But the aurora is not static. It moves, it dances, it pulses and flickers and changes shape, and understanding why requires us to think about what is happening in the magnetosphere, about the constant battle between the solar wind and Earth's magnetic field, about the ways energy flows through invisible plasma currents high above our heads. The traveler in the snow watches as the green curtains begin to fold and ripple. The light intensifies, spreads across more of the sky. A vertical ray shoots upward, perfectly straight, like a searchlight pointing into space. The aurora is coming alive, and somewhere, far above in the thin air of the thermosphere, atoms are glowing. There is something profound about watching light being created, not reflected light, not light from a bulb or a fire, but light that is generated in the moment by the fundamental interactions of matter and energy. This is what the aurora represents, Every photon emerging from the night sky above the Arctic is brand new, created within the last second by an atomic event that has never happened before and will never happen again in exactly the same way. The process begins with velocity, the charged particles descending along Earth's magnetic field. Lines are not drifting slowly downward, they are screaming into the atmosphere at speeds that would cross the continental United States in less than a second. An electron traveling at 30,000 kilometers per second carries tremendous kinetic energy, and when it encounters the thermosphere, that energy must be transferred somewhere. The thermosphere is a strange place. It exists between about 80 and 600 kilometers above Earth's surface, far beyond where commercial aircraft fly, far beyond where weather occurs, but not quite in the vacuum of space. The air here is incredibly thin. At sea level, every cubic centimeter of air contains about 25 quintillion molecules. In the thermosphere, that number drops to just a few billion per cubic centimeter. For comparison, the best laboratory vacuums on Earth are denser than the thermosphere. But those few billion molecules per cubic centimeter are enough. They are oxygen molecules, nitrogen molecules, and individual atoms of both elements floating freely. At sea level, these molecules are constantly colliding with each other, billions of times per second. In the thermosphere, a single molecule might travel several kilometers before encountering another one. This is called the mean free path, and it makes the thermosphere behave very differently from the air we breathe. When a high energy electron from the solar wind enters this environment, it begins interacting with the molecules it encounters, not through direct physical contact in the way we normally think of collisions, but through electromagnetic forces. The electron carries a negative charge, and the molecules contain both positive nuclei and negative electron clouds. As the solar electron approaches, it feels the electromagnetic fields of the atmospheric molecules, and they feel its field in return. What happens next depends on how close the encounter is and how much energy the solar electron carries. In many cases, the electron simply deflects the atmospheric molecule slightly, transferring a small amount of kinetic energy and continuing on its path. These interactions heat the thermosphere, which is why temperatures here can reach 1500 degrees Celsius during solar storms. Even though the air is so thin, you would freeze to death because there are not enough molecules to transfer that heat to your body. But some collisions are more dramatic. Sometimes the solar electron comes close enough to an oxygen or nitrogen atom to interact directly with the electrons orbiting that atom's nucleus, and this is where quantum mechanics takes over. Electrons and atoms do not orbit randomly. They exist in specific energy levels, each level corresponding to a different distance from the nucleus and a different amount of energy. These levels are quantized, meaning electrons can only exist at certain specific energies, never in between. It is like a staircase where you can stand on the steps, but not in the empty space between them. When the solar electron transfers energy to an atmospheric atom, one of that atom's electrons absorbs the energy and jumps to a higher level. The atom is now in an excited state, holding more energy than it would under normal circumstances. This state is unstable. The atom wants to return to its ground state, its lowest energy configuration, and the only way to do that is to release the excess energy. The excited electron falls back down to its original level, and as it does, the energy difference between the two levels is emitted as a photon. a particle of light. The color of that light is determined by the energy difference, which is determined by which levels the electron jumped between. This relationship is precise and unchanging. Every oxygen atom in the universe, when excited in exactly the same way, will emit exactly the same color of light. For oxygen atoms at the altitudes where most auroras form, between 100 and 150 kilometers, the most common transition produces green light at 557.7 nanometers. This happens when an oxygen atom is excited to a specific energy level and then falls back down. The process takes about 3/4 of a second, which might seem instant but is actually quite slow by atomic standards. This delay is important because it means the oxygen atom must remain undisturbed for nearly a second to emit its green photon. At sea level, this would never happen. The air is so dense that the excited oxygen atom would collide with another molecule within nanoseconds, losing its energy through that collision instead of by emitting light. But in the thin thermosphere, the oxygen atom has time. It floats in near vacuum, holds its excited state, and then releases a green photon that begins its journey downward toward human eyes watching from the ground. At higher altitudes, above 200 kilometers, where the air is even thinner, oxygen atoms can access a different transition that produces red light at 630 nanometers. This transition takes even longer, up to 2 minutes in some cases. The atom must remain completely undisturbed for 2 minutes before it emits its photon. This is possible only in the extreme vacuum of the upper thermosphere, which is why red auroras appear at the highest altitudes and are often faint and diffuse. Nitrogen adds complexity to the color palette. Nitrogen molecules can be ionized by the solar particles, losing an electron entirely. When this happens, the ionized nitrogen emits blue light at 428 nanometers. If the nitrogen is excited but not ionized, meaning its electrons jump to higher levels but remain bound to the atom, it emits purplish red light at several wavelengths between 650 and 680 nanometers. These nitrogen emissions typically occur at lower altitudes, below 100 kilometers, where nitrogen is more abundant relative to oxygen. The result is a vertical color gradient. At the highest altitudes, rare red oxygen emissions. Below that, the common green oxygen emissions. The bottom edges, blue and purple nitrogen emissions. The aurora is essentially a layered atmosphere made visible, each altitude glowing with its characteristic color based on which atoms are present and which quantum transitions are occurring. But understanding the colors is only part of the story. The aurora does not just glow uniformly across the sky. It moves, it forms structures, curtains, rays, arcs, coronas. It pulses and flickers. It can brighten from nearly invisible to brilliant in seconds, then fade just as quickly. These movements and structures tell us about the invisible processes happening in the magnetosphere, about the flow of energy and particles along magnetic field lines, about the dynamic interaction between Earth and the Sun. The curtain structure, those vertical sheets of light that look like fabric hanging in the sky, form along magnetic field lines. Remember that the field lines near the poles point downward at steep angles. The particles follow these field lines as they descend, creating vertical columns of ionization and light from the ground, Looking northward toward the auroral oval, we see these columns edge on, and they appear as curtains. The curtains are not actually solid or continuous. They are made up of many individual rays, narrow beams of light that can be as small as 100 meters across. Each ray represents a field-aligned current, a flow of electrons moving along a single magnetic field line. Hundreds or thousands of these rays clustered together create the appearance of a curtain. These rays can be remarkably straight and vertical, extending from near the horizon to overhead. They can stretch for hundreds of kilometers, remaining parallel to each other, and they can move rapidly, swaying back and forth or marching across the sky like a wave. The movement reflects changes in the magnetosphere in the distribution of particles being funneled down the field lines, in the strength and direction of electric fields in the ionosphere. Arcs are simpler structures, smooth bands of light stretching across the horizon. They form when particle precipitation is relatively uniform along a line of latitude. Arcs are often the first sign of auroral activity, appearing as a faint green glow on the northern horizon. As activity increases, the arcs can brighten, develop structure, break up into curtains and rays. A corona is one of the most spectacular auroral forms. It occurs when the aurora is directly overhead and you are looking up along the magnetic field lines. The curtains and rays all converge at a point above you, radiating outward in all directions, like the petals of a flower or the spokes of a wheel. Coronas happen during intense geomagnetic substorms when particle precipitation extends far enough south that observers at relatively low latitudes find themselves directly beneath the auroral oval. The motion of the aurora, the way it pulses and flickers and waves, is caused by fluctuations in the particle flow. The solar wind is not steady. It varies in density, in speed, in the strength of its magnetic field. These variations create pressure waves in the magnetosphere, compression and rarefaction, which affect how many particles are being funneled into the atmosphere at any given moment. More particles mean brighter aurora. Fewer particles mean dimmer aurora. The result is a pulsing, breathing display. Some auroral forms pulse with surprising regularity, brightening and dimming every few seconds. These pulsating auroras are thought to be caused by waves in the magnetosphere interacting with the trapped particle populations. Other forms flicker rapidly, changing brightness on timescales of a tenth of a second. These flickering auroras remain somewhat mysterious, possibly related to instabilities in the current systems flowing through the ionosphere. There are also black auroras, regions of darkness within bright auroral displays. These appear as dark bands or patches that move through the glowing regions. They represent areas where particle precipitation has temporarily stopped, though the mechanism that creates these gaps is still being studied. Every auroral display is unique. The specific combination of colors, structures, and movements depends on the solar wind conditions, the state of the magnetosphere, the season, the time of night, and pure chance. You can watch the aurora 100 times and never see the exact same display twice. Each event is a fingerprint, a unique record of the space weather conditions at that moment. The traveler in the snow is watching this uniqueness unfold. The green curtains have brightened significantly. They now stretch from the western horizon to the eastern horizon, a glowing wall of light that seems impossibly tall. Vertical rays shoot upward from the curtains, some of them reaching almost to the zenith. The light is bright enough now that the traveler can see color with their naked eyes, not just in photographs. The green is vivid, almost electric, and along the top edge of the brightest curtains, there is a hint of red, a dark crimson fringe that flickers in and out of visibility. The snow on the ground reflects the green light, giving the entire landscape an otherworldly glow. Shadows shift and move as the aurora pulses. There is still no sound. Despite old legends claiming the aurora crackles and hisses, there is only silence. The displays occur far too high in the atmosphere for any sound to reach the ground. What the traveler hears is their own breathing, their heartbeat, and the profound quiet of the Arctic night. And high above, atoms continue their dance, oxygen glowing green, nitrogen adding purple highlights, each photon a message from the sun, delivered across 93 million miles of space, transformed by Earth's magnetic field into something beautiful, something that should not exist, but does, something that reminds us we live on a planet in space, connected to a star, part of a system larger than we can fully comprehend. The display is building towards something. The curtains are moving faster now. The aurora never stands still. Even when it appears as a gentle arc on the horizon, barely visible to the eye, it is moving, shifting, breathing. The curtains ripple like fabric caught in a breeze that does not exist. They fold and unfold. They brighten and fade. They seem almost alive, responding to forces we cannot see or feel from the ground. This movement is not random. It tells a story about what is happening hundreds of kilometers above our heads, about the invisible currents of plasma flowing through the magnetosphere, about the constant push and pull between the solar wind and Earth's magnetic field. Every wave, every pulse, every sudden brightening is a visible manifestation of processes that operate on scales too large to comprehend. Scientists categorize auroral movements into different types based on their appearance and behavior. There are discrete auroras, which have sharp boundaries and clear structure. There are diffuse auroras which glow softly without distinct edges. There are pulsating auroras which brighten and dim rhythmically. And there are flickering auroras which change on timescales faster than the human eye can easily follow. The most common movement people notice is the wave motion of curtains. The curtains appear to ripple from one side to the other, like a flag waving in the wind. These waves can travel at speeds of several kilometers per second, moving along the length of the curtain from east to west, or west to east. The waves are actually density variations in the particle precipitation, regions where slightly more or slightly fewer electrons are hitting the atmosphere. As these density variations move along the magnetic field lines, we see them as waves of light moving along the curtain. Sometimes the curtains develop folds. The smooth arc of light develops kinks and curves, creating a structure that looks like drapery hanging in the sky. These folds form when the magnetic field lines themselves become distorted by currents flowing through the ionosphere. The field lines twist slightly, and the particle precipitation follows the twisted field, creating the folded appearance. The vertical rays that shoot upward from curtains can move independently. Individual rays can brighten, then fade, then brighten again. They can appear to march along the curtain, one after another, lighting up in sequence. This marching motion is caused by waves in the magnetosphere, propagating along the auroral oval, triggering particle precipitation at different locations in sequence. One of the most dramatic movements is the auroral substorm. This is not just a brightening of the aurora, but a complete transformation of the entire display. Substorms typically begin with a relatively quiet arc on the northern horizon. The arc is stable, barely moving, glowing softly green. This is called the growth phase, and it can last for tens of minutes or even hours. Then suddenly, the arc explodes into motion. This is the expansion phase. The aurora brightens dramatically within seconds. The arc breaks up into rapidly moving curtains and rays. The auroral oval expands toward the equator, bringing the aurora further south. The brightness can increase by a factor of 100 or more. The entire sky can fill with moving light. During the expansion phase, the aurora takes on a chaotic appearance. Curtains fold and twist. Frays shoot upward and then disappear. New structures form and dissolve within minutes. The light can be so bright that you can read by it, that it casts distinct shadows on the snow. Colors intensify. The green becomes almost neon. Red appears at the tops of curtains. Purple edges develop at the bottom. This phase lasts perhaps 10 to 20 minutes, though it can feel both longer and shorter when you are standing beneath it. The sheer amount of activity, the constant change, makes it difficult to process everything you are seeing. Your eyes dart from one part of the sky to another, trying to take it all in, knowing that what you are watching will never happen again in quite this way. Then comes the recovery phase. The intense activity begins to subside. The curtains slow their motion. The brightness decreases. The aurora retreats northward, back toward its quiet arc configuration. But it does not simply turn off. It fades gradually, becoming more diffuse, losing its sharp structure. This recovery can take an hour or more. What causes these substorms? The answer lies in the magnetotail, that long stretched out portion of Earth's magnetosphere on the night side. During the growth phase, energy from the solar wind is being stored in the magnetotail. The magnetic field lines are being stretched and twisted like winding up a spring. Electric currents build up. Particles become trapped in specific regions. Eventually, the system becomes unstable. The stretched field lines suddenly snap back, reconnecting in a process that releases the stored energy all at once. This energy goes into accelerating particles toward Earth, creating the sudden increase in particle precipitation that we see as the expansion phase. It is like releasing a wound upspring. All that stored energy converts into motion in an instant. Not all auroral activity involves substorms. Sometimes the aurora simply varies in intensity without going through the dramatic expansion phase. These variations can be caused by smaller scale changes in the solar wind, by the rotation of Earth carrying observers through different parts of the auroral oval, or by waves and instabilities in the magnetosphere that do not involve full substorm dynamics. Pulsating auroras are particularly interesting. These appear as patches of light, often irregular in shape, that turn on and off with remarkable regularity. The pulsations can have periods ranging from a few seconds to tens of seconds. You can watch a patch brighten, hold steady for a moment, then fade to near invisibility, then brighten again, over and over. These pulsations can continue for hours, covering large areas of the sky. The mechanism behind pulsating auroras involves waves in the magnetosphere called chorus waves. These are very low frequency electromagnetic waves that interact with electrons trapped in Earth's magnetic field. The waves scatter the electrons, causing them to precipitate into the atmosphere in pulses that match the wave frequency. The result is an aurora that quite literally blinks at you. Flickering auroras are even faster, changing brightness on timescales of a tenth of a second or less. These are difficult to observe with the naked eye because they happen so quickly, but they show up clearly in high speed video. The exact cause of flickering is still debated, but it likely involves instabilities in the electric currents flowing through the auroral ionosphere. There is also the phenomenon of auroral omega bands, named because their shape resembles the Greek letter omega. These are large scale structures that form during the late stages of substorms. They appear as a series of curves or waves that move slowly westward across the sky. Each omega band can be hundreds of kilometers across and can persist for hours. They are thought to be related to instabilities in the boundary between the auroral oval and the lower latitude regions. The speed of auroral motion varies enormously. Some structures move slowly enough that you might not notice the motion unless you watch for several minutes. Other structures race across the sky faster than your eyes can follow. The fastest auroral motions are associated with what are called auroral arcs, thin ribbons of light that can shoot across the sky at speeds exceeding 10 kilometers per second. These arcs are manifestations of intense electric fields in the ionosphere, accelerating particles and creating narrow channels of bright emission. One aspect of auroral motion that surprises many first time observers is that the aurora often moves toward you. When you are watching curtains on the northern horizon, they can suddenly surge southward, spreading overhead. The southward expansion during substorms can be startling. What was a distant glow on the horizon suddenly becomes a corona directly above you, with rays radiating outward from a point in the zenith. The three-dimensional nature of the aurora becomes apparent when you realize that what looks like motion along the horizon is actually motion in altitude as well. The curtains are not flat surfaces. They have depth. They extend through a range of altitudes from about 100 kilometers up to 500 kilometers or more. When the particle precipitation shifts to higher or lower altitudes, the colors and brightness change even if the horizontal position remains the same. Photography captures the aurora differently than the human eye sees it. Long exposure images accumulate light over many seconds, creating smooth blended colors and structures. The motion of the aurora during the exposure creates blurred streaks and softened edges. The result is often more colorful and dramatic than what you see with your naked eye, but it also loses the sense of motion, the dynamic quality that makes the aurora so mesmerizing to watch in person. The human eye is better at detecting motion and changes in brightness than a camera is at capturing them in a single frame. When you watch the aurora, you see it breathe. You see the waves propagate. You see the sudden flares of brightness. You experience it as a four-dimensional phenomenon, changing in space and time simultaneously. This is something that no photograph or video can fully convey. The traveler in the snow is experiencing this now. The curtains that were confined to the northern horizon have spread across half the sky. They are moving rapidly, rippling and folding. Individual rays brighten and fade. The entire display pulses, brightening for a few seconds, then dimming slightly, then brightening again. The rhythm is irregular but persistent, like the aurora is breathing. And then, without warning, everything changes. The curtains suddenly surge upward and southward. The brightness increases dramatically. Within 10 seconds, the entire sky from horizon to horizon is filled with moving light. The traveler finds themselves standing at the center of a corona, looking up into a tunnel of green light radiating from directly overhead. The rays converge at the zenith, creating the illusion of depth, as if the aurora extends upward forever into space. The light is bright enough to see colors clearly now. Green dominates, but there are hints of pink and purple at the edges. The red fringe at the top of some rays is more visible now, a deep crimson that flickers like distant fire. The entire display is in motion, rays moving, curtains rippling, the corona rotating slowly clockwise. This is the expansion phase of a substorm. Somewhere high above in the magnetosphere, field lines have reconnected. Energy stored over the past hour has been released in an instant. Particles are raining down on the atmosphere in unprecedented numbers, and the result is this, one of nature's most spectacular displays happening right now, visible to anyone who happens to be standing in the right place at the right time. The traveler stands transfixed. Time seems to stop. Nothing exists except the sky and the light and the overwhelming sense of witnessing something far larger than human scale. This is what it looks like when a planet and a star interact. This is what happens when magnetic fields collide. This is the universe showing off. And it is not over yet. The northern lights are not democratic. They do not appear everywhere with equal frequency. They favor certain places on Earth, certain latitudes, certain longitudes. If you want to see the aurora, you cannot simply wait for it to come to you. You must go to where it lives. And where it lives is determined entirely by the geometry of Earth's magnetic field. The auroral oval is a ring of light that encircles each magnetic pole. In the north, this ring is centered not on the geographic North Pole, where all lines of longitude converge, but on the North Magnetic Pole, which is currently located in the Canadian Arctic north of Hudson Bay. The magnetic pole moves over time, drifting westward at a rate of about 50 kilometers per year. This movement is caused by changes in the flow of molten iron deep within Earth's core, the same flow that generates the magnetic field in the first place. It generates the magnetic field in the first place because the magnetic pole is not at the geographic pole. The auroral oval is not centered on the top of the planet. It is offset. And this offset means that some locations are far more favorable for aurora viewing than others. Cities at the same latitude can have vastly different auroral activity depending on their longitude. Fairbanks, Alaska, sits almost directly beneath the auroral oval. The city is at 64 degrees north latitude, and the magnetic pole is positioned such that the oval passes right over Fairbanks on most nights. The result is that Fairbanks sees auroras more than 200 nights per year. Not every night, and not always spectacular displays, but visible auroral activity on most clear nights from September through April. Tromsø, Norway is another city blessed by geography. And 69 degrees north, it sits well within the auroral zone. The city markets itself as one of the best places in the world to see the northern lights, and this is not an exaggeration. From late September to late March, when the nights are long and dark, Tromsø residents can see auroras several times per week during solar maximum, and several times per month even during solar minimum. Reykjavik, Iceland, is at 64 degrees north. Similar to Fairbanks, the city sits near the southern edge of the auroral oval, which means that auroras appear on the northern horizon frequently, but overhead displays are less common. However, Iceland's position in the North Atlantic means that clouds and storms can interfere with viewing more often than in the drier climates of interior Alaska or northern Scandinavia. Northern Canada, particularly the territories of Yukon, Northwest Territories, and Nunavut, offers excellent aurora viewing. Cities like Yellowknife have become aurora tourism destinations. Yellowknife sits at 62 degrees north and is positioned such that the auroral oval frequently passes overhead. The city also benefits from being far from ocean moisture sources, resulting in clear skies more often than coastal locations. Northern Scandinavia, including parts of Sweden, Finland, and Norway above the Arctic Circle, all sit within the auroral zone. Towns like Kiruna in Sweden, Rovaniemi in Finland, and Alta in Norway regularly see auroral displays. These locations have the advantage of infrastructure and accessibility while still being remote enough to have dark skies. Scotland and the Northern Isles, particularly Orkney and Shetland, occasionally see auroras during periods of moderate to strong geomagnetic activity. These displays typically appear on the northern horizon rather than overhead. For residents of Scotland, seeing the aurora is a special event rather than a regular occurrence. Russia has vast territories within the auroral zone. The entire northern coast of Siberia, from the Kola Peninsula in the west to the Chukchi Peninsula in the east, experiences frequent auroral activity. However, these regions are sparsely populated and difficult to access, which means fewer people witness the displays despite their frequency. The southern auroral oval, centered on the south magnetic pole, behaves similarly but has far fewer human observers. The south magnetic pole is located off the coast of Antarctica, and the auroral oval mostly passes over the Southern Ocean and Antarctica itself. Tasmania in Australia occasionally sees the aurora australis on its southern horizon. The southern tip of New Zealand, particularly Stewart Island, and parts of the South Island, can see southern lights during strong geomagnetic storms. Southern South America, including parts of Patagonia in Chile and Argentina, can see aurora australis during active periods. The Falkland Islands and South Georgia Island in the South Atlantic are well positioned within the southern auroral zone, but are remote and sparsely populated. Antarctica research stations regularly observe the southern lights. Bases like McMurdo Station, Amundsen Scott South Pole Station, and various coastal stations see auroral displays frequently during the Antarctic winter when the continent is in constant darkness. The key factor in aurora visibility is geomagnetic latitude, not geographic latitude. Geomagnetic latitude measures how far you are from the magnetic poles rather than the geographic poles. The auroral oval typically extends from about 65 to 75 degrees geomagnetic latitude. During quiet times, the aurora stays within this range. During geomagnetic storms, the oval expands toward the equator. Moderate geomagnetic storms, those with a KP index of 5 or 6, can push the aurora down to about 55 degrees geomagnetic latitude. This brings auroral visibility to southern Alaska, southern parts of the Canadian provinces, and the northern tier of U.S. states, including Montana, North Dakota, Minnesota, Wisconsin, and Michigan. In Europe, moderate storms make the aurora visible across Scotland, southern Scandinavia, and occasionally northern England. Strong geomagnetic storms, with KP7 or higher, can push the aurora down to 45 degrees geomagnetic latitude or lower. These events can make the aurora visible across much of the northern United States, including Washington, Oregon, Idaho, Wyoming, Nebraska, Iowa, Illinois, Indiana, Ohio, Pennsylvania, and New York. In Europe, strong storms can bring aurora visibility to northern France, Germany, Poland, and other mid-latitude countries. Extreme geomagnetic storms are rare, but dramatic. The Carrington event in 1859 pushed the aurora down to tropical latitudes. Reports came in from Cuba, Jamaica, and Hawaii of brilliant red auroras filling the sky. The storm was so powerful that the aurora was visible during daylight hours in some locations. Telegraph systems around the world failed. Auroras were reported from as far south as Colombia and Singapore. More recently, the Halloween storms of 2003 produced auroras visible across much of Europe and the United States, including sightings from Texas, Florida, and the Mediterranean. These storms caused satellite anomalies, power grid disturbances, and widespread disruption to GPS and communications systems. The location of auroral displays also depends on local time. The auroral oval is not symmetric. It is wider and more active on the night side of Earth than on the day side. This means that aurora activity peaks around midnight local time, though displays can begin as early as late evening and continue until dawn. The few hours around midnight are statistically the most likely time to see bright auroras. Seasonal factors matter as well. The aurora occurs year round, but visibility requires darkness. In the high Arctic during summer, the sun never sets, making aurora viewing impossible, despite the fact that auroral activity continues overhead. Conversely, during winter, the long nights provide many hours of darkness for potential aurora viewing. This is why aurora season in the north runs from roughly September through April, with December and January offering the longest nights but also the coldest temperatures and sometimes the worst weather. The equinoxes in March and September show slightly elevated auroral activity compared to the solstices. This is called the Russell-McFerrin effect, and it has to do with the geometry of how Earth's magnetic field is tilted relative to the solar wind during different seasons. The spring and fall equinoxes create more favorable conditions for solar wind magnetic field coupling with Earth's field, resulting in more frequent and intense geomagnetic storms. Light pollution is the enemy of aurora viewing. Even a bright aurora can be washed out by city lights. To see the aurora at its best, you need to be away from urban areas, away from street lights and buildings. The darker your viewing location, the more detail and color you will see. A faint aurora that is invisible from the city suburbs can be clearly visible from a rural location just 50 kilometers away. Cloud cover is the other major obstacle. The aurora occurs at altitudes of 100 to 500 kilometers, far above the clouds. But clouds between you and the aurora will block your view entirely. Aurora forecasting is only useful if the sky is clear. This is why interior locations like Fairbanks and Yellowknife have advantages over coastal locations. They tend to have clearer skies on average. The traveler in the snow chose this location carefully. Far from any town, far from any artificial light, the nearest road is 30 kilometers away. The nearest building is abandoned, dark, irrelevant. Here, the sky is truly dark. The Milky Way is visible as a bright band across the southern sky. And when the aurora appears, there is nothing to compete with it, nothing to dilute its light. Now, as the substorm reaches its peak, the traveler understands why this remoteness matters. The aurora fills the entire sky. Every direction shows moving light. If there were city lights on any horizon, they would be trivial compared to this. The aurora is the only light source that matters, turning night into a strange green twilight where shadows shift and dance. This is what the planet looks like when you remove the noise of civilization. This is what has been happening in the Arctic for billions of years, long before humans existed to name it or understand it. The magnetic field and the solar wind locked in their eternal interaction, creating light as a side effect, and for anyone willing to travel to the right latitude, to wait in the cold and the dark, the reward is this: a front row seat to a cosmic event. Color is information. Every hue in the aurora tells us something specific about the altitude, the atmospheric composition, and the energy of the particles causing the glow. The aurora is not just beautiful, it is a diagnostic tool, a visible spectrum analysis of the upper atmosphere happening in real time above our heads. Green is the color everyone knows. It dominates aurora photographs and appears in almost every display. This green comes from oxygen atoms at altitudes between 100 and 150 kilometers. When an electron from the solar wind collides with an oxygen atom at these altitudes, it excites the atom to a specific energy level. The excited oxygen atom holds this energy for approximately zero point 0.7 seconds, then releases it as a photon with a wavelength of 557.7 nanometers. This wavelength falls in the middle of the green portion of the visible spectrum. The human eye is particularly sensitive to this wavelength. Our vision evolved under sunlight, and green wavelengths are abundant in the spectrum of light that reaches Earth's surface. We can detect green light at lower intensities than we can detect red or blue. This is part of why the green aurora is so prominent. It is not necessarily that green emissions are stronger than other colors, but that our eyes are better at seeing them. The 557.7 nanometer transition is called a forbidden transition in atomic physics. This does not mean it is prohibited, but rather that it would not normally occur under high-density conditions. At sea level, an excited oxygen atom would collide with other molecules within nanoseconds and lose its energy through that collision rather than by emitting a photon. But at 100 kilometers altitude, the air is thin enough that the oxygen atom can remain undisturbed for the zero point 0.7 seconds needed to complete the transition. Red auroras appear at higher altitudes, typically above 200 kilometers. This red color also comes from oxygen, but from a different transition. Excited oxygen atoms at these extreme altitudes emit light at 630 and 636 nanometers, which appear as a deep red to our eyes. These transitions are even more forbidden than the green transition, taking up to 110 seconds to complete. Only in the extreme vacuum of the upper thermosphere can oxygen atoms remain undisturbed long enough to emit these red photons. Red auroras are less common than green for several reasons. First, There are fewer oxygen atoms at 200 kilometers than at 100 kilometers. The air is thinner, so there are fewer targets for the solar particles to hit. Second, the red emissions are fainter because the transition probability is lower. Third, human eyes are less sensitive to red light, especially at night when our vision shifts toward rod cells that are more sensitive to blue and green. A red aurora that would appear brilliant in a long exposure photograph might be nearly invisible to the naked eye. When red auroras do appear prominently, they are often described as blood red or crimson. They can fill the entire sky during intense geomagnetic storms. Historical accounts of the Carrington event describe red auroras so bright they were mistaken for distant fires. People in the Rocky Mountains thought the sunrise had come early because the red glow was so intense. The height at which emissions occur affects not just the color, but also the appearance. Lower altitude green auroras have sharp edges and fast motion because the air is denser and the particles interact more frequently. Higher altitude red auroras appear more diffuse, with softer edges and slower motion. They often form a red cap above the green curtains, a distinct layer visible in photographs even when faint to the eye. Blue and purple colors in the aurora come from nitrogen. Nitrogen molecules can interact with solar particles in two ways. If the collision ionizes the nitrogen, removing an electron, the nitrogen ion emits blue light at 428 nanometers. If the collision merely excites the nitrogen without ionizing it, the molecule emits a range of wavelengths in the red and purple part of the spectrum. Blue auroras are typically seen at the lower edges of displays, below 100 kilometers, where nitrogen becomes more abundant relative to oxygen. The blue has a distinct quality, different from the green above it. It is a deep electric blue, almost cyan in intense displays. Combined with the green and red, the result can be a complete vertical rainbow stretching from horizon to zenith. Purple or magenta auroras also come from nitrogen, but from the excited rather than ionized state. Tis appear as a pinkish purple fringe, often at the very bottom of curtains, or as a diffuse glow separate from the main display. The purple can mix with the green to create unusual teal or turquoise hues in some parts of the sky. Very rarely, observers report seeing yellow or orange auroras. These are not distinct emission lines, but rather the result of multiple colors blending together. When green and red emissions occur in the same line of sight, separated by altitude, the colors can combine to create yellow or orange hues. True yellow emissions from other atmospheric constituents are theoretically possible, but have not been definitively observed. The intensity of colors varies with the energy of the incoming particles. Higher energy particles penetrate deeper into the atmosphere before depositing their energy. Lower energy particles deposit their energy at higher altitudes. This means that the color distribution shifts during different phases of auroral activity. During the quiet growth phase of a substorm, you might see only pale green arcs. During the active expansion phase, bright greens appear along with red tops and purple bottoms as particles of all energies rain down simultaneously. Cameras see aurora colors differently than human eyes. Long exposure photography accumulates light over many seconds, bringing out faint reds and purples that are below the threshold of human night vision. The result is that photographs often look more colorful than the aurora appeared in person. This is not fake or exaggerated. The colors are really there. Our eyes simply cannot detect them at low light levels. Modern cameras with high sensitivity sensors can capture auroral colors in real time video, showing motion and color simultaneously. These videos reveal details invisible to the eye, such as rapid color changes as the particle energy distribution shifts, or the three-dimensional layering of different colored emissions at different altitudes. The colors also depend on viewing angle. When you look at a curtain edge on, you see green because you are looking through the densest part of the emission region at 100 to 150 kilometers. When you look straight up through a corona, you might see more red because your line of sight passes through the higher altitude emission regions for a longer distance. The three-dimensional structure of the aurora becomes apparent when you pay attention to how colors change with viewing geometry. Some observers have reported auroras that appear white or colorless. These are typically very faint displays where the light level is too low for the eye's color receptors to function. The rod cells in our retinas, which dominate in low light conditions, are not sensitive to color. Only when the aurora brightens sufficiently do the cone cells activate and color becomes visible. What appeared as a white glow suddenly resolves into vivid green as the display intensifies. There are also rare reports of auroras with unusual colors that do not fit the standard oxygen and nitrogen emissions. Some of these may be related to other trace atmospheric constituents. Hydrogen produces red emissions at 656 nanometers, distinct from the oxygen red. Helium can produce yellow and green lines. These elements are present in tiny quantities in the upper atmosphere, and their emissions are usually too faint to notice, but during extreme events, they might contribute to the color palette. The traveler in the snow is watching the color palette shift in real time. The corona overhead is predominantly green, bright enough that the color is obvious even without dark adaptation. But at the zenith, at the very top of the corona where the rays converge, there is a distinct red glow. It pulses with the green, brightening and fading in sync. Along the northern horizon, where the curtains are lower and more distant, there is a purple tint at the bottom edges, a hint of the nitrogen emissions occurring at lower altitudes. The entire display is in motion, and the colors shift as the structures move. A ray that appears pure green suddenly develops a red top as the particle precipitation shifts to higher altitudes. A curtain that was green and purple gains a pink tint as nitrogen emissions intensify. The aurora is not a static painting, but a dynamic light show where the palette changes moment to moment. And all of this color, all of this beauty, is just atoms doing what atoms do. Oxygen and nitrogen, the same elements you are breathing right now, glowing hundreds of kilometers above your head because they absorbed energy from particles that left the sun yesterday. The colors are physics made visible, quantum mechanics painted across the sky, and you do not need to understand the science to appreciate the beauty, but understanding the science makes the beauty even more profound. Long before anyone understood what the northern lights actually were, humans watched them and wondered. For thousands of years, people living beneath the auroral oval looked up at the dancing lights and created stories to explain them. These stories reveal something important about how we make sense of mystery. When confronted with something beautiful and inexplicable, we weave it into the fabric of our beliefs, our fears, our hopes. The Norse people of Scandinavia saw the aurora as something both beautiful and ominous. In their mythology, The lights were reflections glinting off the armor and weapons of the Valkyries. These were the warrior maidens who served Odin, the chief of the gods. Their task was to fly across battlefields, choosing which fallen warriors were worthy of entering Valhalla, the great hall where heroes would feast and fight until Ragnarok, the end of the world. When the aurora blazed across the winter sky, the Norse believed the Valkyries were riding out, making their selections. The brighter and more active the display, the more significant the battle must have been. There was honor in this interpretation, but also terror. If the Valkyries were riding, it meant men had died in battle. The aurora became associated with warfare, bloodshed, and the thin line between life and death. The Norse also called the aurora the Bifrost, the rainbow bridge connecting Midgard, the world of humans, to Asgard, the realm of the gods. This bridge was said to shimmer with many colors, just as the aurora does. It was a pathway for the gods to travel between worlds, and for the souls of the dead to ascend to their final resting place. In this interpretation, the aurora was not threatening but sacred, a visible connection between mortal and divine realms. Further north, the indigenous peoples of the Arctic had their own explanations. The Inuit of Alaska, Canada, and Greenland did not share a single unified belief about the aurora, but many of their stories shared common themes. Some groups believed the lights were spirits of the dead, particularly those who had died violently or unexpectedly. These spirits were said to be playing games in the sky, sometimes with a walrus skull as a ball, other times simply dancing and celebrating. In some Inuit traditions, the aurora was treated with caution. Children were warned not to whistle at the lights, not to wave their hands or draw attention to themselves. The spirits in the sky might notice you, might come down to take you with them. There was a sense that the aurora existed in a liminal space between the world of the living and the world of the dead, and crossing that boundary uninvited was dangerous. Other Inuit groups had gentler interpretations. Some believed the lights were spirits of animals, particularly seals, whales, and caribou. These animal spirits danced in the sky as a sign that hunting would be good, that the animals were plentiful and willing to give themselves to the hunters. In this view, a bright aurora was a blessing, a promise of survival through the long Arctic winter. The Sami people of northern Scandinavia, the indigenous inhabitants of the region the Norse later settled, had complex relationships with the aurora. Some Sami communities believed the lights were dangerous, manifestations of the souls of the dead that could harm the living. There were taboos against singing or joking under the aurora, against making noise that might attract the attention of the spirits. If the aurora appeared particularly bright or red, it was seen as a bad omen, a warning of violence or death to come. Red auroras especially carried dark connotations across many cultures. The color resembled blood, and when the entire sky turned crimson during intense geomagnetic storms, it was easy to see why people interpreted this as a sign of impending disaster. Medieval European chronicles are filled with accounts of blood-red skies appearing before battles, plagues, or the deaths of kings. The aurora became a celestial messenger, a warning written in light. The Finnish name for the northern lights is Revantalit, which translates to foxfires. This name comes from a legend about a magical fox running across the fells of Lapland. The fox's tail swept through the snow, sending sparks flying into the sky. These sparks became the aurora. In some versions of the story, The fox's fur itself glowed, and the lights were reflections of the fox racing through the heavens. This explanation is gentler than many others, turning the aurora into something playful rather than ominous. In what is now Russia, Siberian indigenous groups had diverse interpretations. Some believed the aurora was fire from celestial hearths, the homes of spirits or ancestors keeping warm in the sky. Others saw the lights as spirits of powerful shamans traveling between worlds. The aurora's appearance could signal that a shaman was conducting an important ritual, that communication with the spirit world was particularly strong that night. Indigenous peoples of North America beyond the Arctic also had aurora traditions. The Cree called the lights the dance of the spirits. The Algonquin believed the aurora was their creator god Nanabojo, reminding them that he was watching over them. Some Plains tribes associated the aurora with the spirits of great warriors, or the northern lights of council fires in the sky. Across the Pacific, in regions where the aurora was rarely visible, it became the stuff of myth rather than regular observation. Chinese astronomers recorded unusual lights in the northern sky as early as 2600 BCE, but these events were so rare at Chinese latitudes that they were treated as extraordinary omens. The lights were sometimes described as dragons, sometimes as divine chariots, always as messages from heaven, requiring interpretation by scholars and priests. The scientific understanding of the aurora began much later and came slowly. In ancient Greece and Rome, the occasional aurora visible at Mediterranean latitudes was noted but not systematically studied. The Roman philosopher Seneca described curtains of light in the sky, comparing them to flames or torches. Aristotle mentioned them in his Meteorologica, categorizing them among atmospheric phenomena like clouds and rainbows, which was not entirely wrong, given that the aurora does occur in Earth's atmosphere. The term aurora borealis was coined by Galileo Galilei in 1619. He combined Aurora, the Roman goddess of dawn, with Boreas, the Greek god of the north wind. Galileo had observed reddish glows in the northern sky and believed they were sunlight reflecting off the upper atmosphere. His explanation was incorrect, but his terminology stuck. The aurora borealis became the formal name for the northern lights in scientific literature. In 1716, Edmund Halley, the astronomer famous for his comet, proposed that the aurora was caused by magnetic effluvia, some kind of luminous material moving along Earth's magnetic field lines. He was remarkably close to the truth, though he had no way of knowing what this effluvia actually was or where it came from. He correctly associated the aurora with magnetism, which was a significant insight. The connection between the sun and the aurora began to emerge in the 19th century. In September 1859, British astronomer Richard Carrington was observing sunspots when he noticed a sudden bright flash on the sun's surface. This was the first recorded observation of a solar flare. Within hours, telegraph systems around the world began experiencing problems. Operators reported receiving electric shocks from their equipment. Telegraph paper spontaneously caught fire in some offices. And that night, one of the most spectacular auroral displays in recorded history lit up skies around the world. Carrington suspected a connection between the solar flare he had observed and the subsequent auroral activity. He published his observations and suggested that something from the sun had traveled to Earth and caused the geomagnetic disturbance. Most of his contemporaries were skeptical, But Carrington had made a crucial connection. The sun and earth were not isolated from each other, they were linked. The actual mechanism remained mysterious for decades. In the 1890s, Norwegian scientist Christian Birkeland proposed that electrons from the sun were responsible for the aurora. He even constructed an apparatus called a terrella, a magnetized sphere in a vacuum chamber, and demonstrated that electron beams directed at the sphere created glowing regions near the poles. His experiments were remarkably prescient, essentially creating artificial auroras in his laboratory. But Birkeland's ideas were controversial. Many scientists of his era believed that space was empty, that nothing could travel from the sun to Earth except light. The concept of electrically charged particles streaming through space seemed outlandish. Birkeland died in 1917 without seeing his ideas fully accepted. The vindication of Birkeland's work came with the space age. In the 1950s and 1960s, satellites began measuring the environment around Earth directly. They detected the magnetosphere, the solar wind, and the flow of charged particles into the polar regions. Everything Birkeland had proposed turned out to be correct. The aurora was caused by electrons from the sun, guided by Earth's magnetic field, colliding with atmospheric atoms. The mythology and the science represent two different approaches to understanding the same phenomenon. The ancient stories sought to place the aurora within a framework of meaning, to connect it to human concerns like death, warfare, and the favor of the gods. The scientific explanation seeks to understand the physical mechanism, to trace the chain of causation from the sun to the glowing atoms in our atmosphere. Neither approach diminishes the aurora. The science does not make the lights less beautiful or less worthy of wonder. If anything, understanding that you are watching particles from the sun colliding with oxygen atoms hundreds of kilometers above your head makes the experience more profound. You are seeing a tangible connection between Earth and the sun, a reminder that we live in a solar system, that our planet does not exist in isolation. The traveler in the snow thinks about this continuity. Countless humans over thousands of years have stood in this same position, watching these same lights, feeling this same sense of awe. The explanations have changed, but the experience has not. The aurora still stops you in your tracks. It still makes you feel small and connected simultaneously. It still creates a moment where nothing else matters except the light dancing above you. Somewhere, right now, someone is seeing the aurora for the first time and inventing their own explanation for it. Maybe a child asking their parent what causes the pretty lights. Maybe someone who never believed the aurora could be as spectacular as the photograph suggested. The aurora continues to inspire wonder, continues to make people question and explore and feel something larger than their daily concerns. This is what endures. Not the specific stories, not the exact physics, but the human response to mystery and beauty, the need to understand, to explain, to share the experience with others. The aurora has always done this, and it always will. We live in an era where the aurora has been thoroughly explained, yet remains deeply mysterious. We understand the basic mechanism, the journey of particles from sun to atmosphere, the quantum transitions that produce light. We can predict when geomagnetic storms will arrive, can track the solar wind in real time, can forecast auroral activity hours or days in advance. And yet, standing beneath the lights, all that knowledge feels incomplete. There are questions we still cannot answer, details that elude our instruments, subtleties that surprise us. The modern study of the aurora relies on a network of satellites, ground stations, and scientific campaigns that span the globe. In space, satellites positioned at the L1 Lagrange point between Earth and the Sun monitor the solar wind constantly. The Advanced Composition Explorer, launched in 1997, sits approximately 1.5 million kilometers from Earth, measuring the speed, density, and magnetic field of the incoming solar wind. When a coronal mass ejection passes ACE, scientists on Earth receive about 30 to 60 minutes of warning before it hits the magnetosphere. Other satellites in polar orbits pass directly through the auroral zones, measuring particle fluxes, electric and magnetic fields, and the emissions from the aurora itself. The Themis mission, a constellation of 5 satellites, has revealed much about magnetospheric substorms by simultaneously measuring conditions at different locations. They have shown that substorms begin with a process called magnetic reconnection in the magnetotail, just as theory predicted, but the details are far more complex than anyone expected. On the ground, arrays of cameras and magnetometers track auroral activity continuously. Networks like the All Sky Imager Array in North America capture images of the entire visible sky every few seconds from multiple locations. By comparing images from different stations, scientists can triangulate the altitude and three-dimensional structure of auroral features. These measurements have revealed that what looks like a simple curtain from the ground is actually an incredibly complex structure with fine detail down to scales of 100 meters or less. Magnetometers measure variations in Earth's magnetic field caused by the currents flowing through the ionosphere during auroral activity. These currents can be enormous, millions of amperes flowing in sheets through the ionosphere at altitudes around 100 kilometers. The currents create magnetic fields that can be detected on the ground, and by measuring these fields at multiple locations, scientists can map the current systems and understand how energy flows through the magnetosphere. Incoherent scatter radar facilities in places like Alaska and Scandinavia bounce radio waves off the ionosphere and measure the returning signal. This technique reveals the temperature, density, and motion of the plasma in the ionosphere during auroral events. The data shows that the aurora is not just a visual phenomenon, but a region of intense heating and turbulence, with atmospheric temperatures increasing by hundreds of degrees and winds reaching speeds of several kilometers per second. All this instrumentation has revealed that the aurora is far more than pretty lights. It is a manifestation of a complex system of energy transfer from the solar wind to the magnetosphere to the ionosphere to the atmosphere. The energy budget is staggering. A moderate auroral substorm dissipates about 100 gigawatts of power, roughly equivalent to the entire electrical generating capacity of the United Kingdom. A major storm can dissipate 10 times that amount. This energy deposition affects the atmosphere in ways we are still learning about. The heating during auroral events creates upwelling in the thermosphere, pushing the atmosphere to higher altitudes. This increases drag on satellites in low Earth orbit, causing their orbits to decay faster than expected. After major geomagnetic storms, satellite operators must adjust orbital parameters to compensate. The electric currents flowing through the ionosphere during auroral activity can induce currents in long conductors on the ground, power lines, pipelines, and railway tracks can all experience geomagnetically induced currents during storms. In extreme cases, these currents can cause transformers to overheat and fail, leading to widespread power outages. The most famous example occurred in March 1989, when a geomagnetic storm knocked out the entire power grid in Quebec, leaving 6 million people without electricity for 9 hours. The storm induced currents in the grid that caused protective relays to trip and transformers to fail. The entire system collapsed in less than 2 minutes. Similar but less severe effects have been reported in other countries during major storms. Modern power grids are designed with this risk in mind. Operators can take protective measures when storms are predicted, such as reducing load, bringing extra transformers online, or temporarily disconnecting vulnerable equipment, but the risk remains. A Carrington level event today would overwhelm these protections. Some studies estimate that repairing the damage from an extreme geomagnetic storm could take years and cost trillions of dollars globally. Satellites are particularly vulnerable. High energy particles can penetrate satellite electronics, causing glitches or permanent damage. Solar panels degrade faster during storms due to particle bombardment. In 1994, two Canadian telecommunications satellites failed during a geomagnetic storm, causing widespread service disruptions. Since then, satellite operators have become more cautious, putting satellites into safe mode during predicted storms. GPS accuracy degrades during auroral activity because the ionosphere becomes turbulent and irregular. Radio waves passing through the ionosphere are refracted differently than normal, creating positioning errors. For most consumer applications, this is merely an annoyance, but for applications requiring precision, such as surveying or automated aircraft landing systems, it can be serious. Airlines sometimes reroute polar flights during major storms to avoid communication blackouts and GPS degradation. Radio communications are also affected. High frequency radio waves that normally bounce off the ionosphere can be absorbed during auroral activity, creating radio blackouts. This particularly affects communication with aircraft flying over polar regions where satellite coverage is limited. Amateur radio operators, on the other hand, sometimes welcome geomagnetic storms because they create unusual propagation conditions that allow long distance contacts on frequencies that normally would not work. Beyond these practical concerns, studying the aurora advances our understanding of plasma physics and magnetospheric dynamics. The processes that create the aurora occur throughout the universe. Jupiter and Saturn have powerful auroras driven by interactions between their magnetic fields and their moons. Other stars likely have stellar winds that interact with their planets. Understanding Earth's aurora helps us understand these distant systems. The aurora also serves as a natural laboratory for plasma physics. The conditions in the magnosphere and ionosphere during auroral events are difficult or impossible to reproduce in laboratory experiments. Studying the aurora teaches us about magnetic reconnection, wave-particle interactions, and turbulence in ways that apply to fusion energy research and astrophysics. For most people, though, the scientific value of the aurora is secondary to its aesthetic value. Aurora tourism has grown dramatically over the past 2 decades. Tens of thousands of people travel to Alaska, Iceland, Norway, and other auroral zone locations every winter specifically to see the northern lights. Hotels advertise aurora wake up calls. Tour companies run multi day excursions into the wilderness. Photographers spend weeks chasing the perfect shot. This tourism brings economic benefits to remote northern communities, but also creates environmental and social pressures. Popular viewing areas can become crowded. Light pollution from tour buses and hotels interferes with viewing. There are questions about sustainability and about how tourism affects local communities and ecosystems. Some locations have embraced aurora tourism more successfully than others. Iceland has developed extensive infrastructure without overwhelming its fragile environment. Yellowknife in Canada has positioned itself as an aurora capital while working to preserve the wilderness that makes the experience possible. Tromsø in Norway balances tourism with scientific research, hosting both visitors and auroral observation facilities. The democratization of photography has changed how people experience the aurora. Everyone with a smartphone can now take photos that would have required expensive equipment a generation ago. Social media is flooded with aurora images, some spectacular, some ordinary, all representing someone's moment of connection with the phenomenon. This has both positive and negative effects. More people are inspired to see the aurora themselves, but there is also a sense that the aurora has been commercialized, turned into a commodity to be captured and shared rather than simply experienced. The traveler in the snow has not taken a single photograph. The camera sits in the bag, unused. There will be time for photos later, or perhaps there will not. Right now, the only thing that matters is watching, being present, letting the experience unfold without the distraction of framing shots and adjusting settings. The substorm has reached its peak. The entire sky is alive with motion. Curtains stretch from horizon to horizon, rays shoot upward. The corona overhead rotates slowly, colors shift and blend, and in this moment, all the science, all the history, all the mythology fades into irrelevance. There is only the light and the darkness and the overwhelming sense of witnessing something that transcends human concerns. This is what the aurora offers: a moment of pure experience, unmediated by explanation or technology. A reminder that beauty exists in the universe, that mystery remains despite our knowledge that we are small parts of a vast interconnected system. The aurora does not care whether you understand it or not. It simply is, has always been, will always be, and you are here, now watching it dance. Eventually, all auroral displays end. The particle flux decreases, the magnetic field lines relax, the glow fades from the sky, leaving only stars and darkness. What was brilliant minutes ago becomes a memory, something you carry with you but can never fully recreate for someone who was not there. The aurora is ephemeral, existing only in the moment, and perhaps that is part of what makes it so precious. The traveler in the snow watches as the display begins to subside. The recovery phase has begun. The corona that filled the overhead sky breaks apart, resolving back into separate curtains that drift northward. The brightness decreases. The rapid motion slows. Within 10 minutes, the spectacular display has returned to a simple arc on the northern horizon, glowing softly green, barely moving. This arc will persist for another hour or more, slowly fading as the geomagnetic storm weakens. Eventually, it too will disappear, and the sky will return to its normal state, empty of aurora but full of stars. The Milky Way reasserts itself as the dominant feature, a river of light flowing across the southern sky. Overhead, constellations that were invisible during the bright aurora now emerge: Cassiopeia, Ursa Major, Polaris the North Star. The cold reasserts itself as well. During the height of the display, the traveler forgot about the temperature, about numb toes and stiff fingers. The adrenaline and awe provided their own warmth. But now, standing in the post aurora darkness, the chill returns. It is 20 degrees below zero, maybe colder with the wind. Time to head back, to return to shelter and warmth in the ordinary world of human concerns. But before leaving, there is a moment to reflect, to think about what just happened, what it means, why it matters. The aurora is just physics, just particles and atoms and electromagnetic fields following natural laws. And yet, it is also more than that. It is a visible connection between Earth and the Sun, a reminder of our place in the solar system. It is a phenomenon that has existed for billions of years, that will continue long after humanity is gone. It is beauty created without intent, spectacle without audience, unless we choose to watch. The aurora teaches humility. Standing beneath it, you cannot help but feel small. The curtains stretch hundreds of kilometers. The energy involved dwarfs anything human civilization can produce. The system that creates the aurora, from the nuclear fusion in the sun's core to the magnetic field generated by Earth's molten iron core to the thin atmosphere where light is produced, operates on scales that defy easy comprehension. We are brief, tiny observers of a vast cosmic machine, but the aurora also teaches connection. The same processes that create the dancing lights affect our technology, our power grids, our satellites, our communications. We are not separate from space weather. We are part of the system, inhabitants of a planet that exists in the flow of the solar wind. The sun touches us, quite literally. Every photon of light, every solar particle, every magnetic field fluctuation links us to our star. The indigenous peoples who created stories about the aurora understood something important. The lights are liminal, existing at the boundary between Earth and space, between the known and the unknown, between the mundane and the transcendent. They remind us that the universe is stranger and more beautiful than our daily experience suggests. There are forces at work, processes unfolding, events occurring beyond our perception, unless we know where to look and when. Modern science has given us the where and when. We can predict storms, can track particles, can explain the colors and motions in exquisite detail. But science has not removed the sense of wonder. If anything, understanding the mechanism makes the aurora more remarkable. The fact that we can trace a photon from a nuclear fusion reaction in the sun's core through the solar wind along magnetic field lines to an excited oxygen atom in the thermosphere to our eyes and explain every step of that journey is itself awe-inspiring. We live in an age where mystery is optional. You can look up any question and find an answer within seconds. The sum of human knowledge is accessible from anywhere on Earth, and yet there are still experiences that transcend knowledge, that remain profound, no matter how well you understand them. The aurora is one of these experiences. You can study it for years, can memorize every detail of the physics and chemistry, and still find yourself standing speechless beneath the dancing lights. Perhaps this is because the aurora operates on timescales that match human perception. Unlike most cosmic events, which happen too slowly or too quickly to watch, the aurora unfolds in human time. You can see it move. You can watch structures form and dissolve. You can follow rays as they shoot upward. The aurora is accessible in a way that most phenomena are not. You do not need instruments or computers or years of data analysis. You just need to be in the right place at the right time and look up. This accessibility is precious. In a world increasingly mediated by screens and devices, the aurora remains a direct experience. You cannot reproduce it in virtual reality. You cannot fully capture it in photographs or videos. The scale is too large, the motion too complex, the emotional impact too personal. You have to be there, physically present, standing in the cold and the dark, looking up at the real sky. And this requirement for presence makes the aurora something rare in modern life, an experience that cannot be downloaded or streamed. The traveler in the snow understands this now, if they did not before. Whatever expectations brought them to this remote location, whatever images they had seen or stories they had heard, the reality exceeded all of it. Not because the aurora was more spectacular than expected, though it was, but because being there is fundamentally different from seeing representations of being there. The three dimensionality, the motion, the sound of silence, the smell of cold air, the feel of frozen ground beneath boots, all of these combine to create an experience that exists only in memory and cannot be fully shared. And yet, people try to share it. The aurora shows up in art, in poetry and music. It appears in films and photographs and virtual reality experiences. Every culture that has encountered it has tried to capture its essence, to communicate what it feels like to watch the sky come alive with light. These attempts always fall short, and perhaps that is appropriate. Some things should remain beyond full description, should retain an element of mystery that can only be resolved through direct experience. The aurora also reminds us of time, geological time, astronomical time, the deep time of planetary processes. The magnetic field that funnels particles toward the poles has existed for billions of years, generated by the slow convection of molten iron deep beneath our feet. The sun has been streaming particles into space for just as long and will continue for billions of years into the future. The auroras we see tonight are part of a continuous process that predates humanity and will outlast us. But there is also human time. The Inuit, who watched these same lights thousands of years ago, the Norse warriors who interpreted them as messages from the gods, the Victorian scientists who first proposed the connection to the sun, the satellite engineers who monitor them today to protect infrastructure, the tourists who travel from around the world to witness them, all of us, across time and culture, connected by our shared response to this phenomenon. As you lie in bed tonight, about to drift into sleep, imagine that somewhere above the Arctic, the aurora is dancing. Right now, at this very moment, oxygen atoms are glowing green. Nitrogen is adding blue and purple highlights. Curtains are rippling in the solar wind. Someone is standing in the snow, watching in awe, feeling small and connected simultaneously. You do not need to be there to be part of it. The aurora exists whether anyone watches or not, but knowing it exists, understanding how it forms, appreciating its beauty and significance, that is a form of connection. You are lying beneath the same magnetosphere that creates the lights. The same solar wind flows past your planet. The same magnetic field protects you. You are part of the system, a participant in the cosmic dance, even if you cannot see the light it produces. Let this knowledge settle into your thoughts as sleep approaches. The universe is vast and ancient and filled with processes beyond immediate perception. But sometimes, in certain places, under certain conditions, those processes become visible. Beauty emerges from physics. Light appears in darkness. Mystery and understanding coexist. The aurora is a gift, not given intentionally, not created for our benefit, but a gift nonetheless, a consequence of planetary and stellar processes that just happens to be visible, that just happens to be beautiful, that just happens to inspire wonder in conscious minds that evolve to appreciate such things. Sleep well knowing that above the Arctic, the dance continues, that particles from the sun are still finding their way to Earth, that oxygen will glow green again tomorrow night, and the night after, and the night after that, the aurora is eternal, patient, indifferent to whether we watch. But for those who do watch, for those who make the journey to the cold places where the lights appear, the reward is an experience that changes how you see the world. You are part of a planet orbiting a star. You are protected by a magnetic field generated by processes deep underground. You are bathed in a solar wind that occasionally becomes visible as dancing light. And you are capable of understanding all of this while still feeling wonder at its beauty. That is the real gift, not just the aurora itself, but the capacity to appreciate it, to study it, to be moved by it. As consciousness fades and sleep takes over, let the image of the aurora carry you into dreams. Green curtains waving in the darkness, red fringes flickering at the heights, purple edges at the base, the silent majesty of light without sound, the gentle reminder that Earth is not separate from space, but immersed in it, connected to the sun, part of the vast cosmic system that created us and sustains us. The northern lights are dancing tonight. They are always dancing somewhere, and that is enough. That is everything. Sleep now beneath the memory of that light and know that beauty exists in the universe, that wonder is real, that some things remain magnificent no matter how well we understand them. Good night.